The future quantum internet will be a huge quantum network. In such a network, we process quantum information in nodes and exchange information carriers through communication links. We need robust carriers for that. For this purpose, the tiny entities that make up light are suited best. We call them photons. It is a familiar fact that matter is made of the tiny entities that we call atoms. It is perhaps less familiar that light is made of photons. So, let us review how we know that there are photons. This is really a question about the nature of light, a question that was answered during the 19th and the early 20th century. Let us recall the contributions of the main actors. In the early 1800s, Young's double-slit experiment and other experiments as well strongly suggested that light has properties analogous to water waves and sound waves. Among others, Fresnel took this suggestion seriously and turned it into a working hypothesis that allowed quantitative predictions. Now, that Fresnel's method reproduces the data of Young's experiments is not a serious test, as the scientific method does not permit the testing of a hypothesis by the data that first suggested it. Rather, we must predict and then test new phenomena from the hypothesis, and a wholly unexpected new phenomenon provides particularly strong support for the hypothesis. In Fresnel's case, this came quickly and with a splash, when Poisson predicted a bright spot at the center of the shadow of a circular obstacle, a ball or a disk, which he regarded as absurd. But within days, Arago demonstrated that this Poisson spot is really there. The year is 1818. Later, by the way, Arago had a distinguished career as a public servant and politician. Given Poisson's skeptical prediction and Arago's convincing demonstration, should we, perhaps, call the bright center the Arago spot rather than the Poisson spot? This is a moot point really, for it turns out that Poisson's spot had already been discovered a century earlier by Delisle and confirmed by his mentor Maraldi. But this discovery did not get attention and was well forgotten when Young, Fresnel, Poisson and Arago entered the stage. Well, history is not always fair. Then, in the 1860s, Maxwell established a celebrated set of equations that give a complete and consistent account of all electric and magnetic phenomena. In particular, Maxwell predicted that there are electromagnetic waves that propagate at the speed of light, which had already been measured quite accurately by Fizeau and Foucault. But one needed additional experiments to confirm that there really are electromagnetic waves and that light is composed of such waves. Such experiments were conducted by Hertz. In Hertz's experiment, a battery feeds current into a transformer, and the induced current in the secondary coil charges two huge capacitors. When the switch is suddenly opened, the capacitors release the stored charge, and a spark bridges the gap. This miniature lightning is the source of an electromagnetic burst wave that is picked up by the receiver with its spark micrometer. In way of summary then, the combined efforts of Young, Fresnel, Poisson, Arago, Maxwell and Hertz established that light is composed of electromagnetic waves with an octave of wavelengths for the colors of visible light, as well as the longer wavelengths in the infrared and the shorter wavelengths of the ultraviolet radiation. The nature of light appeared to be fully understood. But then, within the short period of 2 decades, 2 new classes of phenomena pointed to properties of light that were not accounted for as yet. These concerned the photoelectric effect and the thermal properties of light. We turn to them now. The so-called photoelectric effect was discovered by Hertz while he was testing the equipment for his experiments in the 1880s. In a circuit with a gap, where no electric current flows, one can trigger sparks across the gap by shining ultraviolet light on the wire ends. Further studies of the photoelectric effect by other researchers followed. In particular, in 1902, Englert reported his observation that the electrons emitted from illuminated surfaces had energies determined by the wavelength of the light, not by its intensity, as Maxwell's equations would imply. Englert's work was, of course, only possible after Thomson had discovered the electron 5 years earlier and established that currents flowing through wires result from electrons moving through the metals. In Englert's experiment, light of a well-selected color illuminates a metal surface and the electrons are released after absorbing energy supplied by the light. The electrons are caught by an electrode and the resulting current is recorded. On the way from the surface of the electrode, the electrons pass through a wire grid where a negative voltage can be applied which prevents slow electrons from reaching the electrode. If the voltage is too high, if it exceeds the critical value, the electrons do not reach the electrode and no current flows. Englert observed a strict relation between the color of the light and the critical voltage. Maxwell's electromagnetism could not account for Englert's observation, although the photoelectric effect clearly is an electromagnetic phenomenon. Something was amiss, something big. Englert's stunning observation caught Einstein's attention and led to his seminal 1905 article on the photoelectric effect. But Einstein's big step forward had a second stepping stone, namely Planck's radiation law. For this story, we return to the early 1890s. While research on the photoelectric effect was ongoing, others, in parallel developments that were partly initiated by Maxwell himself, studied the thermal properties of electromagnetic radiation by the tools that had been applied successfully to other physical systems such as gases. A blacksmith knows that iron turns first red, then yellow, when heated up before shaping. So the dominant wavelength of the radiation is shorter for higher temperatures. We want to address this issue quantitatively and invoke an analogy. You fill a container with gas at a certain temperature, then measure the pressure and compare the results with your expectations. You let a thin beam of gas escape through a small hole in the wall and check whether the velocity distribution is that predicted by theory. Quite similarly, you can fill a container with electromagnetic radiation at a certain temperature and observe the escaping light, that is, the light emitted through a tiny opening, or perhaps emitted by the surface of a hot object. Can we be more specific about this? What is the dominant wavelength for the given temperature? We want to give an answer that refers solely to the properties of the radiation, but not to the material that emits it. For this purpose, we imagine an ideal object that absorbs all radiation that hits it, whatever the wavelength, and otherwise is characterized by the temperature. We call this a black body. It can be realized in a laboratory with great accuracy. A standard construction, pioneered by Wien and others in the 1890s, traps light inside a cavity and observes the radiation that escapes through the small opening. Now, what about the radiation emitted by such a black body? How are temperature and color related? The very same Wien took a shot at this problem by combining, quite ingeniously, several partial insights from thermal physics and Maxwell's theory. Wien arrived at a clever, educated guess. Wien's mathematical expression worked well for the shorter wavelengths for which data were available at the time. How about longer wavelengths? They required additional experimental techniques. New measurements were completed in 1899 and reported by Pringsheim and Lummer and quickly confirmed by others. Let us take a closer look at the data for 1449 Kelvin, about 100 degrees above the melting point of gold or copper. These new data demonstrated once more that Wien's relation between temperature and color was accurate for short wavelengths. But the data for longer wavelengths were at odds with what Wien's formula says. This disagreement was crying out for an explanation. Max Planck enters the stage. Planck had been trying, without success, to justify Wien's formula by a clear-cut demonstration on the basis of the established laws of physics. And now the new data made it clear that Wien's formula was not fully correct. So rather than a justification of Wien's formula, one needed an improvement. And Planck delivered. He announced his celebrated formula in October 1900, although he himself was not fully convinced of the arguments that led to the result. Planck gave an improved justification in the months that followed, but in his own words, he had to resort to an act of desperation, ein Akt der Verzweiflung. The energy associated with a particular color of light comes in multiples of tiny units and cannot take on intermediate values. So Planck's improvement of Wien's formula got the matter right, also for radiation with long wavelengths. And in that range it agreed with the answer given by Rayleigh and Jeans, who had applied standard methods of thermal physics to Maxwell's equations. Their result was quite alright for very long wavelengths, but disagreed totally with Wien's formula for short wavelengths. In summary, Planck's famous result is correctly approximated at short wavelengths by Wien's formula and at long wavelengths by the Rayleigh-Jeans expression. All was fine then, except for Planck's act of desperation. Its full justification came later, after the first quarter of the 20th century had elapsed. We now reach 1905, when Einstein recognized how Planck's act of desperation had a bearing on Lenard's observations about the photoelectric effect. Lenard found that the energy of electrons set free from a metal is directly linked to the wavelength of the light that illuminates the metal surface. The shorter the wavelength, the larger the electron energy. Planck found it necessary to ascribe tiny basic units of energy to each color. The shorter the wavelength, the more energy per unit. If Planck is right about energy available in small bits, in quanta that is, then, so Einstein reasoned, one should expect that Lenard's electrons absorb the light energy in these portions and acquire an energy related to the wavelength exactly as Lenard had observed. In effect, Einstein concluded that the grainy, particle-like nature of light is not just a convenient mathematical fiction in Planck's toolbox, but an actual property of light. Light really consists of individual quanta, tiny, indivisible lumps of energy that can only be traded in whole. At the time, this was quite a revolutionary concept. We now have two completely independent experimental facts: Planck's blackbody radiation and Lenard's photoelectric effect. As Einstein demonstrated, both find a natural explanation if light is made up of tiny building blocks, quanta of light, much like matter is composed of atoms. The wave nature of light, established in the experiments of Young, Arago and many others, and an integral part of Maxwell's electromagnetism, is supplemented by particle properties. Ever since we speak of the wave-particle duality. There are the electromagnetic waves. We can observe interference patterns such as the fringes of a double-slit experiment, and the waves are made up of tiny lumps of energy, each a quantum of light. An individual light quantum is indivisible. It contributes a tiny bit to the interference pattern, wherever it lands on the observation screen. And all the tiny bits of very many light quanta make up the full interference pattern. A first experiment of this kind, in which the light quanta passed through the apparatus one by one, was conducted by Taylor in 1909. Taylor, in fact, did not investigate diffraction by a double slit, but rather that of a thin needle. Einstein's wave-particle duality was rather controversial when it was new. But remember, about a century before, first chemists and later physicists learned to accept that all materials are made up of atoms, one kind for each chemical element. Now, in 1905 and the following years, they had to accept that light is also composed of quanta, one kind of light quantum for each color. This acceptance was not easy at all, for one profound reason. While there was a mathematical formalism for dealing with waves and a separate formalism for dealing with particles, one could not deal with waves and particles, or with the wave aspects and the particle aspects of one physical object in a consistent way. This union of the continuous and the discrete was finally accomplished in the mid-1920s when Heisenberg and Schrödinger, together with quite a few others, developed the physical concepts and the mathematical formalism of quantum mechanics. And for the light quanta, meanwhile called photons, a term coined by Lewis in 1926, a satisfactory mathematical formalism was not available before the late 1940s. In the 20 years between Einstein's stroke of genius in 1905 and the arrival of quantum mechanics in 1925, more evidence emerged in support of the fundamental particle aspects of light in addition to its wave nature. Let us mention three milestones. First, in 1909, the year of Taylor's one photon at a time experiment, Einstein studied the fluctuations of energy in small volumes occupied by radiation and found that there is a wave-typical contribution and also a particle-typical contribution. Both are needed for consistency with Planck's radiation law. Second, in 1917, Einstein considered the absorption and the emission of photons by atoms, with intrinsic properties of the kind that Bohr had envisioned a few years before, and ensured that the thermal properties of a gas of atoms and those of the radiation are consistent with thermodynamics. This required the recognition of a new process, stimulated emission, which made the construction of lasers possible some 40 years later. Third, in 1922, Compton found that X-rays scattered off atoms, rather off the electrons in atoms, emerge with longer wavelengths, just as the energy transfer in an elastic electron-photon collision requires. Legend has it that Compton's discovery finally convinced the ever-skeptical Planck that photons are real.